Hello everyone, welcome to our poster titled 3D structure based model generation to functionally annotate lytic polysaccharide monooxygenases. I am Aathi Maikandan A from final year of BTech Bioinformatics, Shastra deemed to be University, India. Degradation of the plant biomass is an important goal in several applications. Mixture of biomass degradation enzymes are used in industries for this purpose. Conventional glycosylates hydrolase enzymes fail to act on crystalline polysaccharides, but lytic polysaccharide monooxygenases can oxidatively cleave crystalline polysaccharides. Lytic polysaccharide monooxygenases are a family of enzymes that are copper dependent and oxidative in nature. These LPMOs are commonly known as auxiliary activity enzymes. Auxiliary activity enzymes are further classified into 8 subcategories, namely A9 to A11 and A13 to A17. The chitinolytic enzymes of are mainly classified under A10 family, and cellulolytic enzymes are mainly classified under A9 family. LPMO sequences have a structural similarity of around more than 80 to 90% and a sequence similarity of around 20 to 30%. Thus, the goal of this study is to use the pre-existing 3D structures to train a machine learning model and differentiate LPMOs which can degrade chitin and cellulose. The workflow we developed for the study is starts with the data collection part, data processing, feature extraction, feature selection, and preparing machine learning models and validating them. Coming to the data collection part, we used a carbohydrate active enzyme database to retrieve LPMO sequence information and structural information. We used the in-house developed Python scripts to cross-validate between the information present in KZ and GenBank to come up with the structures with desired features to train a machine learning model. The sequence information we found in KZ were used by converting them into 3D structural files using AlphaFold 2. The statistical data for each and every auxiliary activity family found in KC are represented in table 1. Moving on to the data processing part, most of the structural information present in KG are to be in the format of PDB format. PDB format is basically a 3D coordinate file of protein. We use PyMol, which is a visualizing tool, to convert PDB format into standard triangle language format, which are basically 3D coordinate files representing the geometrical topology. Figure 2 here represents the cartoon structure of finality PDB, and on the right, the same finality PDB as a 3D model. Moving on to the feature extraction, we use the converted SQL files to extract 3D geometrical features. Two ways are implemented in extracting features. One was using Python libraries such as PrimeMesh, Open3D, and NumPy STL, and the other was using a software called Molecular Surface and Molecular Surface package. We were able to get around 34 descriptors representing each and every 3D structure models. And moving on to the feature selection part, we use ensemble feature selection methods, which uses more than 8 different methods to bring up with an normalized ensemble scores for each and every descriptor. We assumed that ensemble score of around 0.6 or above it can be a significant feature that can be used in training a machine learning model. Moving on to the validation part and machine learning model, we created machine learning model with various algorithms such as SVM, naive-Bayes, random forest, logistic regression, and neural network. We used for loop to find the best parameter values by plotting and plot using F1 score values of each and every parameters. Here, the table 2 represents the ensemble feature selection scores retrieved after performing feature extraction. We were able to see that convexity, concavity are the two features with more than 0.6, and we used those two features for training the machine learning model. Here, the figure 3 represents the F1 score plot for SVM model with polynomial function, where we were able to see that the model performs well optimized when the parameter value of C is 5.1 and the gamma is 0.501. And figure 4 here represents the F1 code plot for multi-layer perceptron with ReLU as an activation function and SGD as a solver. The model was well optimized when the learning rate was set to 0.006 and alpha value to 0.001. As for the validation of a machine learning model, we used different performance matrices such as recall, precision, and F1 score to evaluate and optimize the model. Take here, the table 3 represents the simple machine learning classifier models such as SVM, random forest, and naive. We observe that SVM model with polynomial function was able to perform well when compared to other simple machine learning classifier models with a F1 score of 0.97. And moving on to the table 4 represents the neural network algorithm, which is a complex machine learning classifier model where ReLU as an activation function and solver with SGD was able to perform well when compared to other complex machine learning classifier models with an F1 score of 0.90. We generated 24 different machine learning algorithms and we compared between them, and we were able to conclude that SVM was the best performing model for our data set. And at the same time, we were able to prove that 3D structural features extracted from a protein file can be used in annotation of these proteins using machine learning models. Thank you for listening.